Okay, here we're covering lesson 4.2, which is on translations. You've learned so far that translation is a function in which all of the points of a figure move the same distance in the same direction as described by a translation vector. If you've never seen this word vector before, it is simply a fancy word for an arrow. It's a description of a direction and a distance at the same time. So you could imagine an arrow that pointed this direction but was much longer or was much shorter. Those would be different vectors. You could also imagine a vector that was the same length but pointed in different directions than this one. That would also be a different vector. So a vector is defined as a certain distance and a certain direction. Okay, that's how we're going to define it right now. So this vector is telling us how to move our object. It's saying we're going to move it in this direction, this distance. Okay, so specifically we're going to go over 5 up 2. So if you see here, we've gone over 5 up 2 for all of these points, over 5 up 2. When a translation has been applied to a figure, 1, the distance between each pair of corresponding vertices is the same. So B and K are corresponding vertices, C and L are corresponding vertices, A and J are corresponding vertices. They all have the same distance. This distance, which we could find using the Pythagorean theorem if we wanted, we could say that A squared plus B squared equals C squared. So we'd get 5 squared plus 2 squared equals C squared, or 25 plus 4. We get 29 equals C squared, and therefore this distance would be the square root of 29. So in the future, you may be needing to do that, find the actual distance that these things are traveling. But we'd be doing that using the Pythagorean theorem, recognizing that this is one part of a right triangle. Okay, now, the segments that connect each pair of corresponding vertices are parallel. Okay, the segments that connect each pair of corresponding vertices are parallel. So remember, line segment. A segment is a section of a line that's bounded by 2 points. So they're saying they haven't drawn them, but C to L, you could draw a line segment between those 2 points. You could draw one between B and K, which let me just do. So I'm not asking you to imagine these things. And if you draw these line segments, okay, if I draw them, I'm going to get parallel lines. Okay, so these lines, if I continued them, if I drew them well enough, if I just continued them out, they would never cross. These are parallel lines. Poorly drawn parallel lines. Unfortunately, my little smart pen's not working this morning, so I'm trying to draw things with the mouse, and it looks terrible. Finally, recall that translation vector describes the magnitude and direction of the translation. The magnitude of the vector is its length from the initial point to the terminal point. Okay, so we're saying the length of this vector, another word for it is the magnitude. Vectors are not always used to describe just physical distances. There's other kind of vectors, and more generally, we would describe the term magnitude and direction as the 2 things that define a vector. In this topic, the way that we're using it, we're going to be thinking of that magnitude as a length on the graph. So there's a length to the vector, and there is a direction. And as long as you can kind of understand that, I think you should be fine as we move forward. So moving on, we will start example number 1.